All right, welcome everybody to the first part of chapter 13, Properties of Solutions. We're going to go through a couple of pieces of information that introduce what solutions are. Again, this is more of a review than it is an introduction, but we have talked about solutions in general in the past. What we're going to talk about in this chapter is how they are affected by certain factors, as well as a couple of other minor topics surrounding that. So first things first, solutions are generally going to be homogeneous mixtures, meaning you cannot see the parts of two or more pure substances. So solutions can be anything from one solute dispersed uniformly through a solvent to several solutes dispersed uniformly throughout a solvent. And remember that solute means the smaller part and solvent means the larger part. Intermolecular forces is another concept that does come into play here. In particular, we just say that intermolecular forces must be pretty strong when it comes to solute-solvent particles, because otherwise we wouldn't see them separate we would see them separate. In general, major intermolecular forces that are going to be in play are going to involve dipole ion forces, hydrogen bonding, and a couple of other distributed charge-based type things. Always remember that we have those London dispersion forces to contend with as well. Okay, next up is going to be this idea of solvation. So specifically when a solvent surrounds a solute, like in the case of this chlorine and sodium ions on this page down here, the green and the purple, the solvation process really is just a fancy way of saying that each ion gets surrounded by whatever the solvent is, in this case, water. If an ionic compound is the one that is actually soluble in water, it has to do with the ion-dipole interactions that are going to overcome lattice energy. So remember that we talked about how crystal lattices are a thing in ionic compounds, and the lattice energy is the energy that keeps those ions together. So when it comes down to it, the ion-dipole interaction between the different molecules in the solvent-solute interaction is going to have to be larger and large enough and strong enough to overcome that lattice energy that holds those things together. Okay, so there's a couple of different things that we want to talk about when it comes to solutions in terms of the energy that goes along with this. So there's energies that go into different parts of solution physics here. The first is going to be the energy around the separation of the different solute particles. So how much energy is required to pull the salt particles apart from each other. The next is going to be the separation of solvent particles, so how much energy is required to separate the water molecules from each other. And the last is going to be the energy required to actually allow the solute and solvent to interact with each other. Now, all of these energies are going to come together, and we've talked about enthalpy of reaction before, and that's going to be one of our ways to actually describe how the energy and the energetics of this different stuff comes into play. The enthalpy change is going to be delta H. Remember, the delta H of the solute individually and the delta H of the solvent is going to be added together. And then we're going to subtract the delta H of the overall mixing process to get a initial final situation where the delta H of the solution for most solutions is going to be a negative number. Just remember that in this particular case, our things do not tend to occur spontaneously, i.e. without some kind of intervention, unless the energy of the system is very low, okay? So for us, that would mean that the endothermic solution process is not very common. The exothermic solution process is much more common. When things are more spontaneous, we get that exothermic process happening. Endothermic processes do occur, but a lot of times they're not spontaneous is all we're saying. Some of those endothermic processes will happen, but those are more randomized processes. And this is because we're leaving out a piece of the picture. We have to insert an argument for what we call entropy. And that is something we are going to talk a little bit about this semester when we talk about the energetics of things. But that is the second factor in the overall picture. So think puzzle pieces. Enthalpy is a really big puzzle piece, but entropy is another big puzzle piece as well. One of the things that we use to describe entropy is amount of randomness. So how disordered a process or how disordered something is relates to its entropy. So if we have a very disordered process, then it has high entropy. And if we have a very ordered process, it has low entropy. When it comes to the entropy of a system, if we increase the amount of randomness that a system is having, then the overall energy of the system tends to go down as a result. So even though our enthalpy may be telling us a different story, since it's only like half the picture, the overall energy of a system can still go down even if it becomes a more disordered system. So this is going to be one of our first warnings in this particular semester. The first is it's like a misconception alert. So one thing to note is that just because something disappears when it comes into contact with a solvent doesn't mean that it's actually dissolved. In fact, what might have happened is an actual chemical reaction. There is a difference between dissolving and a chemical reaction. The thing we did in lab this week where we dissolved our crystals of benzoic acid and then allowed them to recrystallize, that was just a dissolving crystallization process. There was no reaction. So you have to kind of be aware that dissolution is a physical change, and we want to keep an eye out for the signs of a chemical change always. Remember that one of the major signs of a chemical change happening is, like, for instance, in this particular example, putting nickel metal and hydrochloric acid together ends up forming a nickel chloride compound that is a completely different color than either of the two things you started with. And color change is one of those major signs of a chemical reaction. If you can't get back your original materials, it means an actual reaction did occur. From there, we talk about the different types of solutions that are out there. The first is going to be a saturated solution, which is the simplest way to describe a solution that cannot take on any more solute. We've dissolved as much as we possibly can at whatever temperature the solvent is at that can go into solution. Dissolved solute at that point is in what we call a dynamic equilibrium. Equilibrium meaning that the rate at which the solid particles dissolve and the liquid part and the solid particles go back into a solid form is equal to each other. So the dynamic part means constant movement. So when something is hey, we've got as much as we possibly can dissolved in the solvent, you cannot dissolve any more. In fact, adding any more would just mean it would sit at the bottom. So a good way to think about a saturated solution is if you've ever made Kool-Aid. You initially add the Kool-Aid to that cold water the sugar to the cold water. In order to get it all to dissolve, you have to stir it for a while. And the reason you're stirring it is to get all of that sugar to go into solution. You are creating a saturated solution at that point. If you add much more sugar, the sugar will just hang out at the bottom of that Kool-Aid pitcher. And so we don't want to do that. We do want to create a saturated solution, meaning we can't add any more, but we're not trying to create a super saturated or an oversaturated solution. Anything below the saturated amount is going to be referred to as an unsaturated solution. Most solutions that we will make will be what we call unsaturated because we can continue to dissolve more and more of the solute into the solvent at whatever temperature the solvent is being held at in an unsaturated solution. So think does not have as much as it possibly could hold. Could still take on more sugar if you're thinking about that Kool-Aid example. Next type is going to be what we call a supersaturated solution, and this is actually what we created in lab in order to get crystals to happen. So what we do is we dissolve an amount of solid in a hot or a warmer solvent temperature, and as it cools, it can only take on less than is already dissolved in it. And so what we do is we see this crystallization happening as a result of a supersaturated solution. In other words, the solvent is holding more than it should at the temperature as it goes down, as far as the temperature really going down to, say, room temperature. Okay. One of the ways to think about solubility and or how much will dissolve in something else. And when we use the term solubility, what we're thinking of is how much of this particular solute can dissolve in a set amount of solvent. Well, we can talk about the factors that affect the solubility. The first is going to be the polarity of the substance. So the The saying like dissolves like implies that polar substances like to dissolve in polar solvents. And vice versa, nonpolar substances tend to dissolve in nonpolar solvents. So here's a reason that we can say that most substances dissolve in water, and it's because water is the universal polar solvent, and most substances tend to be polar. Nonpolar substances would need a different type of solvent to be as equally soluble. Okay. Another one's going to be the similar intermolecular attractions. So if, say, you have a compound that does have the ability to do hydrogen bonding and you're trying to dissolve that compound in a solvent that also is able to do hydrogen bonding, like water, then the fact that they both have that intermolecular force in common will affect how soluble that solute or that substance is in that solvent of water. And an example is something like glucose, which is going to be very soluble in water, while something like cyclohexane does not. And so up here on the top, we have cyclohexane. You can see that it has all these hydrogen atoms just kind of floating around it. This is actually what we call a 6-carbon ring. You can't see the carbons, but those are the points on that different structure. So this is a carbon, and 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 so on and so forth. Well, this is a 6-carbon ring with 2 hydrogens on each carbon, and in this particular substance it would not exhibit the hydrogen bonding that we would predict, because remember that hydrogen bonding has to have a hydrogen attached to an oxygen, a nitrogen, or a fluorine. And so this one does not have the ability to do hydrogen bonding, and water, which famously does have the ability to do hydrogen bonding, is not a very good solvent for this type of molecule. This is not a polar solvent, or I'm sorry, a polar substance. This is a very non-polar substance. So it's not going to dissolve in a polar substance. Now, cyclohexane would be really good dissolved in a polar solvent. Think something that has a lot of hydrogen groups or maybe really long chains, and so on and so forth. Down here, we have glucose. The glucose molecule is a really common molecule that you talked about when you were in biology, and that each of these different hydrogen atoms that is attached to an O has the ability to do hydrogen bonding. So look at all these spots on this particular molecule where hydrogen bonding can occur with water. So that is one of the major reasons why we describe glucose as being very soluble in water, aka why it's also one of the major molecules in your body, because you're made up of a lot of water. All right, another one is going to be, again, just solubility of different molecules. So the larger molecules get, right, the more complicated they get, the easier it is to actually kind of describe them as non-polar, because especially if they're made up of the same substance over and over and over again, think about this whole molecule has just the same atoms over and over and over again, just kind of attached to each other with kind of a randomized structure. And then the end has this tiny little hydroxide group, OH, right? Well, this is going to be vitamin A, and since it's mostly non-polar, it's not going to be very soluble in a polar solvent. There's only one area for it to actually be interacting with a solvent like water. Well, on the flip side, we have vitamin C, which is super soluble in water, aka the reason why it's in your orange juice, and the reason why it's easy to ingest a lot of vitamin C when you need to when you're sick is because it's such a easily dissolved in several different types of compounds. It also interacts with your system really easily because, again, water and you go hand in hand. Vitamin A is going to be something that you really can only get through fats in your diet. And so vitamin A is just as important as vitamin C as far as like your system is concerned. You need them both to function well. And vitamin A is one you can't really get in like easily ingested foods unless you're eating a lot of different fats that contain it. Whereas vitamin C, you can go and you can buy like vitamin C gummies at the vitamin area of your grocery store. So just kind of remember that there are a lot of different factors that we can talk about as far as in affecting solubility. One other that I didn't see, but I do want to make sure that I touch on, and we've already kind of talked about it in the course of this one, in this lecture, is temperature. Temperature very much affects the solubility. In other words, at low temperatures, we can dissolve less of our solutes than we can at higher temperatures of the solvent. So the temperature of the solvent makes a difference. It makes a big difference. Gases are going to be kind of different. Gases are a little bit weird in that solubility of gases in water is going to go up if they're heavier compounds. So the heavier the compound and the larger the molecule of the gas is, the more it's going to be able to actually dissolve into something like water. That has a lot to do with the fact that they have bigger intermolecular forces. London dispersion forces go up. Remember, we talked a little bit about that when we talked about intermolecular forces last semester. Intermolecular forces make a lot of difference when it comes to the interaction of molecules with each other and molecules in their environments. And we said that as the molecular mass of something goes up, it becomes, it has stronger molecular interactions. And that's because it's getting bigger too. It has more surface area to interact with its surroundings. So that'll continue to play a part in this particular type of interaction. Another thing that we can notice is that solubility increases with pressure. So for something like oxygen and carbon monoxide, the solubility or the amount of the gas that can dissolve in whatever solution it might be in goes up as we increase the pressure as we get closer to room temperature. This is not the same thing that happens with liquids and gases, because liquids and gases are kind of, I wouldn't say immune, but not as affected by pressure changes as gases are going to be. As the solubility increases, so does the pressure. That is a direct relation. And then, of course, and this is going to be our one of our final topics of today, after we talk a little bit more about temperature, is Henry's law. Henry's law is going to be the relation of how much of the gas can actually dissolve in a set pressure of gas. This relates the solubility of the gas, which is typically given in a unit of like grams per milliliter, to a constant for a specific gas in that solvent. So this is like a specific measured value, and the pressure of the gas. So the partial pressure of the gas above the liquid is the other one that you would need in order to do some of that math. And then we talk a little bit about temperature. Solubility of solid solutes and liquid solvents is going to increase with increasing temperature. Hence why if we wanted to dissolve more sugar in water, we would want to heat the water first. And then, any other type of interaction is true. Same thing with salt. If we want to increase the amount of salt we can dissolve in water, then we want to heat the water first. But remember that temperature, gases are going to behave differently. So if we increase the temperature of a gas, we actually make it less soluble. So this is why you go to pull a soda out of the fridge and it tastes more bubbly if it's been cooled than if you try to drink it warm, right? The warmer your soda is, the less fizzy it is, the less likely you are to want to drink it. This also explains lake turnover and why warmer lakes tend to have less O2 in them. So warmer bodies of water tend to have less oxygen, dissolved oxygen in them, and less like plant life or animal life. I want to say aquatic life, yeah. All right, and so I am going to stop us there. Our second section in chapter 13 is going to go over molarities and calculating those different things. I hope you have a great day. I am going to post some practice problems in your OneNote, so please get that open. And otherwise, you have a great weekend.